All right. Hello, good night, good morning. I want to show just a brief demo or a brief explanation of what I've been working on for those who are interested, and a brief demo of what is occurring there. So let me just exit out of this really quickly. There we go. Try again. All right. So what I've been working on here, if we look at specification really quickly, is utilizing reactive synthesis to tackle this game of cops and robbers, where you have a certain finite grid space and you have a cop agent and a robber agent, and the robber is getting controlled by some sort of input. It could be me or another system, and the cop is being controlled by the system itself. So we're trying to essentially find a system in which a cop agent is guaranteed to catch a robber agent on a finite graph. And we can look at the specification here. This is being done in TSLMT, and now we're utilizing the ISI tool to do this instead of what we had been doing in the past. So we can see here we have to specify some inputs. We're specifying a cop, somewhere on a grid, X and Y, right? It's on the XY axis, robber as well. And then we have some assumptions and guarantees, right? Our assumptions are going to be what we assume about the inputs of the environment going into our system, and our guarantees are what we're guaranteeing about the output the system makes relating to these assumptions or these inputs it received. We can look at that really quickly. We have a grid space, so here we'll define it as this. We have a cop X position. It has to be greater than equal to 0 and less than equal to 6. So this is defining a grid axis, an x-axis of 7 spaces, and likewise we do the same thing with the y. Then we do the same thing with the robber, right? We have to guarantee that the robber is also going to be on this grid. So we're receiving inputs of a cop and robber, and we want to guarantee that they're both on a grid. We're going to ignore this for now. It's important but not important. Now we're going to look at the guarantees. So we have assumptions on our inputs. We make assumptions of what we're receiving. We assume that the robber's in the grid because we don't want the robber to be infinitely far from the grid, because why would I want to catch that? It's not really that important. Assuming that it is in the grid, what do we want to do with that, right? We're going to make some guarantees here and how the cop agent reacts. We have a cop that's going to also be in this finite space, and we can see the same parameters as we had before. It's 7 by 7. Then we say, all right, this cop can make some sort of movements. What are the type of movements we can make here? We'll say that it can move to anywhere in an adjacent cell on this grid. So we can say, one, it can stay the same. It can move left or right. Or, once again, going up and down, it can stay the same or move up and down. We can see that here, add to the y coordinates of the cop by integer 1. So that's how we're essentially specifying here. Now, given that we said that we have a cop on the grid and it can move in any direction, we need some sort of objective as to what it's actually attempting to do here. And we can see that in this last formal statement. This is saying eventually it always holds that the cop and robber will be equal. And more specifically here, it's saying that the x-axis of the cop must equal the x-axis of the robber, and the y-axis must equal the y-axis of the robber, and all that beautiful stuff. And essentially what the specification is saying is that given that we have a cop and a robber and they're both on the grid, we want to guarantee that the cop, maintaining its position in the grid, will move in a way to the next cell at each time step, such that eventually it'll reach the robber and keep up with the robber and maintain the robber for an infinite period of time, as long as your computer can hold battery. But now let's look and see what actually happens, right? When we synthesize this, what's going to occur here. And we have the script that'll do that, but we won't look too much into that. Now what we're going to actually look at is 1, the controller, and 2, the game. So pull up the controller here. This is actually what Izzy is going to create for us, the program, and it's going to be a C program, and it's a very beautiful looking controller. It has a lot of conditionals and a lot of ternary operators, if that's how you pronounce it. I don't remember. Ternary, I don't know. You have these long conditionals. They're beautiful, and we can see that all the way and down here, up and down. And one interesting thing about the way that Izzy generates these is that it kind of throws these read input functions throughout when it needs to read an input, which makes it honestly kind of modular, because we can kind of define what we want the read input function to do. So in this case, I run this on one thread, and the read input function blocks every time it needs to wait for an input, and it'll print out some quick debugging content as well and change the inputs. Then we can go to the game folder and our game file, and we can see what exactly is happening there. We'll see that we create a controller thread that has this controller, and then we can see that we have this main function. This is using raylib in C to generate a finite grid that we can have a cop and robber on. And you can see that when we press down some inputs, we can move the robber, and then, you know, we'll draw the grid, and we'll just continually have the controller running in another thread expecting inputs when we modify these there. And then we'll redraw and keep playing the game. And that's pretty simple, pretty straightforward. Now I'm gonna actually just demonstrate how the game works when we run it. So we can run it here and see what exactly happens. So I can move. It's a little laggy sometimes, I've noticed. But you can see the cop is it's really chasing me, and that's just completely a synthesized controller. And it'll catch me, as it should, because it's formally guaranteed to catch me. That's its one job. And we can see what we do. It's kind of interesting to see how sometimes it zigzags, because we don't really specify the strategy as to how the cop needs to catch the robber. So sometimes it makes kind of movements that you wouldn't maybe think were ideal, but that's the way it found. And kind of still corners you, and eventually will get you. So that's a really fun, interesting thing to do. We can see how this works once again. And there's one interesting game you can play, which I think is more of an error with my specification, or maybe not the specification, but the way it reads inputs, and maybe it reads inputs too late. You can kind of do a little dance. Like the cop won't allow it to be, the cop will never allow the robber to really surrender itself. It will only attempt to catch the robber, but if you try to move to the cop position, it gets really confused and just tries to move away into a position that it can actually catch the robber. And I think that's more an error with how I've made things here, but it is, as we've seen, guaranteed to catch the robber, which is really fun and interesting. And we can also play some other games with that as well. So for instance, we could try a specification where maybe we have an obstacle where the cop and robber can't go into some certain space in the grid. We could have multiple cops, and the main constraint here is that state space definitely expands rapidly when you add more cops in. So for instance, this I haven't actually gotten to synthesize in like a reasonable time, so I'm trying to work to see if I can decrease the grid size. And likewise, when you try to add an obstacle and then add more cops, the state space just goes crazy. So these are really fun and interesting games to play, but that's what I've been working on for anyone who wants to expand off of that. Yeah, good night and good morning.